Hello everyone, I'm Kwan from Nanyang Technological University, Singapore. Today, I'm going to present real-time modeling of observation filter in a remote microphone technique for an active noise control application. The main application of our work is to essentially improve the existing remote microphone technique in an active noise control application when dealing with a changing primary acoustic field. In our work, we shall propose a source tracking method in a remote microphone technique to track changes in the primary acoustic field, which allows the observation filter to be modeled in real time and hence improve its estimation error. In order to understand the impact of our work, we need to first understand the importance of virtual sensing in active noise control applications. In practical application, active noise control often face design constraint in placing its error microphone where control is needed. Human ears are one of the examples, as it is too dangerous to place microphones inside the ears. Additionally, as the frequency increases, the zone of quiet is also becoming smaller. This causes the desired control point to be outside the control zone and thus reducing its active noise control performance. This limitation can be essentially overcome by using a virtual sensing method. The remote microphone technique is one of those methods that uses an observation filter, which is the O in the block diagram over here, to predict the signals at a virtual position through physical monitoring microphones. And the optimal observation filter can thus be expressed in either a time or physical domain given below. The remote microphone technique, however, is sensitive to a change in acoustical field. This may impact the use of remote microphone technique in certain applications, such as the open-aperture active noise control applications, where aircraft noise propagates from the top and traffic noise that propagates from below. As those noises are typically incoherent to each other, the remote microphone technique can be reconstructed based on the source decomposition technique, where we add the spectral density matrix individually based from that source alone. So once we manage to get the correct reconstructed spectral density matrix, we can essentially obtain a new set of observation filter that represent the current noise source in the primary field. This can be also realized in the time domain given here. Notice that this formula includes R and V. And this parameter represents the source ratio, which is defined as the ratio between the current noise source amplitude to the calibrated source ratio. The question is, how do you actually get this parameter for a changing source loudness over time? Our first attempt in tackling this problem is to first investigate on the sensitivity of the source ratio when evaluating the estimation error. Real-time experiments that mimics an open aperture applications placed with monitoring microphones here and the virtual error microphones here. Sorry, monitoring microphones here and error microphones over here. The source will place here represented different noise sources coming from different directions were equipped with incoherent white noise, each having different sets of amplitude. And we put acoustical foam here to ensure that it will be a free field propagation as much as possible. Our first simulation uses two loudspeakers, V1 and V2. After the calibration stage, both V1 and V2 will play incoherent white noise together with a given source ratio. For example, in figure A, loudspeaker 1 will be given a source ratio of 1.2 and the loudspeaker 2 will be given a source ratio of 0.8. And when these two noise sources were playing, the observation filter will essentially take this signal from the monitoring microphone and predict the estimation error. But this time, when during the reconstruction, we will give the wrong source ratio. For example, in figure A, we will be giving 0.8 on this loudspeaker and 1.2 on this loudspeaker instead. It can be seen that as the estimation error increases, the mismatch is getting louder, which is quite apparent in figure B here on the mid frequency where the estimation error degrades quite badly here. This proves the need to estimate the source ratio correctly over time. So how do we actually get the source ratio parameter? We propose in estimating the noise ratio, which involve making use of multiple physical monitoring microphones. So since the correlation matrix R for multiple monitoring microphones can be obtained quickly and we have the true signal of the correlation matrix between the monitoring microphones alone, we can use it to estimate the source ratio by matching the true correlation matrix R with the formulated correlation matrix R hat, constructed by the superposition of incoherent noise source over here. The A and B here serve as a lower and upper bound vector constraint to prevent the Z going out of bound, and we set Z equals to R squared to make it as a quadratic minimization problem. So if you actually notice, this is essentially a matrix L2 norm matching method. So once you formulate the minimization problem, you can essentially estimate the source ratio through an iterative approach given above over here, and we have the final gradient descent approach that correctly predicts the current source ratio based on iterations. The idea behind this is that if the current noise source ratio is correctly predicted to formulate the correlation matrix between monitoring microphones alone, we can use the same noise ratio parameter to eventually predict the correlation matrix between monitoring and error microphones, which allows us to reconstruct the observation filter. As you can see, the optimal observation here given here, and if we have this true method, and we have the source ratio method obtained through this source tracking formulation, we can essentially use the same parameter to estimate the RDMDE, since we also apply the same assumption where all noise sources are incoherent, and once you get the true value of the RDMDE and the R and V is that, we can essentially reconstruct a new set of observation filter based on the current noise source, and these reconstruction filter can essentially be adapted when there is a change in the noise source ratio. To verify this technique, we have performed simulation results based on the measured path from the open-aperture applications. When all 4 loudspeakers were played with a source ratio of 1 and the initial condition given 0, we can see that the algorithm managed to correctly predict the source ratio over time here. It can be also seen that the convergence happens in both the RDMDM and RDMDE, as they are only dependent from the noise source ratio. This verifies the part that we only use the monitoring microphones to predict the source ratio, but the same set of source ratio can be accurately reconstruct a new set of RDMDE instead, which prove the convergence in both the DMDM and the DMDE correlation matrix. This allows us to reconstruct a new set of observation filter. OST represents source track observation filter, and it shows an accurate estimation as the optimal observation filter, and it's very similar to each other. In conclusion, while the observation filter can be reconstructed through the spectral decomposition method, its additional source ratio parameter still remains unknown in real time. Real-time experiments has showed its sensitivity when using the wrong source ratio parameter, leading to a degradation in the remote microphone technique estimation. Our proposed source tracking method is capable to update its source tracking ratio iteratively, and hence allow reconstruction based on its correct source ratio parameter. That's the end of my presentation. If you have any further question, feel free to come to my poster session at Wednesday morning, 7 June 2023. Thank you everyone for listening to my presentation.